Hello everyone, and welcome to my GBUS 1485 Capstone project presentation. I am Zhiyan Zhu, and today I'm excited to share with you our project titled Application of MLP on option pricing prediction. This project represents a accumulation of our learning and research in the field of business and finance, and it aims to showcase how advanced machine learning techniques, specifically multilayer perceptrons or MLPs, can be applied to the complex world of financial analytics. Here listed what you are going to expect. The first section is Introduction. I am excited to share our exploration into the realm of financial analytics, particularly focuses on the accuracy of option pricing models. Historically, the Black-Scholes metal model has been a cornerstone in this field. Despite its widespread use, it has notable limitations, especially in handling complex market behaviors that deviate from its underlying assumptions. Our study marks a significant shift from this traditional approach by integrating advanced computational technique, specifically multilayer perceptrons or MLPs, into the realm of option pricing. The objective of our research is to meticulously compare the performance of MLP neural networks against a conventional Black-Scholes metal model. A key aspect of our investigation revolves around analyzing how MLP adapts across different moneyness intervals, a term that refers to the intrinsic value of options in the market. This is a critical factor in the accurate valuation of options. Our journey through this project was a blend of collaborative teamwork and focused individual efforts. We navigated through various challenges, both conceptual and practical, to arrive at the sites we will discuss today. Let's dive into the intricate world of financial analytics and see how traditional models measure up against modern machine learning techniques. The second section is team organization and personal involvement. Moving on to our team's organization and my personal involvement in this project, the team's dynamic was central to the progression of this research. As a team leader, my role involved not just guiding the direction of the project, but also overcoming a range of challenges that we encountered along the way. Our team was composed of individuals with diverse skills and backgrounds. Michael took the lead in data collection and developed the initial model prototype. Yang, though limited in his coding experience, played a crucial role in gathering the necessary materials for our research. Colin, juggling his undergraduate studies, managed to contribute significantly to our abstract. This team's dynamic evolved, particularly after Michael's departure, which led to a shift on our focus towards the development of the paper with reduced interaction with our sponsor. This change necessitated a greater emphasis on our individual contributions. In my capacity, I introduced a novel aspect to our model, a risk-free predictor. I also concentrated on evaluating the effectiveness of the 10 active functions within our neural network model. This experience was not only a journey of managing a team, but also personal growth, as it involved balancing individual research responsibilities with collaborative team effort. The second section is literature review. Let's dive into the literature review that underpins our project. In the domain of option pricing, the Black-Scholes metal model has long been a benchmark. However, it is important to critically examine its underlying assumptions, which often do not align with real-world market complexity. The evolution of machine learning in finance has opened new frontiers, particularly highlighting the role of multilayer perceptron in financial modeling. MLP represents a significant advancement over traditional models due to their ability to handle nonlinearities and complex market dynamics. Our project situates itself with its evolving landscape. Theorem underscores the potential of neural networks like MLP to approximate a wide range of functions, making them particularly suitable for financial applications where traditional models fall short. Our aim through this research was to rigorously test the effectiveness of MLP against a traditional Black-Scholes model in the specific context of option pricing. In this section, we will dive into the core problem our project addresses and the objective set forth by our sponsor. The primary challenge we faced was to enhance accuracy of option pricing models. The traditional models like the Black-Scholes model has served the financial industry for decades, but they often fall short in handling the non-linear nature of the model. Our focus was to evaluate the effectiveness of multilayer perceptron neural networks across different moneyness intervals, a term that signifies the intrinsic value categories of options. A significant aspect of our project was the selection of appropriate error metrics like root mean square error and mean absolute error to assess the accuracy of our model. Our sponsor was particularly interested in a more transparent and adaptive approach to option pricing, one that could handle the variability across different moneyness intervals more effective than traditional models. Our research direction involved intensive data analysis, categorizing options based on their moneyness, and refining the MLP configuration through iterative testing. We also focused on empirical validation, which involved analyzing the initial graphs and data visualization to understand our model's performance. The goal was to simplify the complex concepts of the MLP model for practical use in financial sector. Section 5 is methodology. Our methodology in crafting the multi-layer perceptron model was both rigorous and systematic. We began by structuring the MLP as a feed-forward network, a critical component in understanding how the model processes and learns from the data. The choice of activity functions was pivotal. We explored the Tan, Sigmoid, and ReLU functions, each with its unique characteristics and implications for the model's performance. One of the challenges we encountered was tackling issues like vanish gradient, a common problem in neural networks that can hinder learning. This led us to scrutinize the impact of learning rates and initializer on the performance of different activity functions within MLP model. Our approach also involved a detailed analysis of the data, categorized it into moneyness interval, which was crucial for testing model on a varying market condition. To access the performance of our model, we employed a range of metrics, including mean squared error, mean absolute error. This empirical approach allowed us to test various MLP configurations, striving to achieve the highest accuracy in predicting option pricing. The methodology was not just about building the model, but about understanding and refining every aspect of it to ensure reliability and effectiveness in a real-world financial context. The section 6 is results. In this section, we discuss the results of our research, particularly focusing on the performance of different activity functions within the MLP model. Our analysis begin with a comparative study of Tan, Sigmoid, and ReLU functions, each offering distinct characteristics that influence the model's overall performance. We examined the impact of neuron count, observing how increasing number of neurons affected the mean squared error trends for each activity function. Similarly, the influence of layer count was analyzed, shedding light on how different numbers of layers affected the efficacy of Tan, Sigmoid, and ReLU functions. The interaction between learning rate and initializer proved to be complex yet insightful, highlighting the nuanced dynamics that play a crucial role in the method's performance. Our comparative analysis extended to juxtaposing the MLP model with the traditional Black-Scholes model, providing a clear perspective on where each stands in terms of accuracy and reliability. Our empirical findings were quite revealing. They challenged our initial hypothesis, particularly regarding the sigmoid function, highlighted the effective of Tan and ReLU function. These results underscore the necessity for exploration and the iterative approach in the development of MLP models for financial application. The seventh section is discussion. Let's move on to discussing the key findings and their implications. One of our main discoveries was the superior performance of the Tan function in option pricing models compared to the sigmoid function. This finding challenges existing presumptions about neural network application in finance, particularly in the context of option pricing. It highlights the critical need for careful selection of active function and network architecture to optimize model performance. The analysis of learning rates and initialize revealed complex interactions that significantly influence MLP performance. Our contribution to the field of knowledge through research in twofold. Firstly, we offer new insights into the interoperability and the reliability of neural network models in financial applications. Secondly, our findings suggest a significant potential for advanced machine learning techniques to revolutionize the way financial analytics are approached, particularly in option pricing. The section 8 is conclusion and the future world. As we conclude our presentation, let's summarize the key outcome and look ahead to future research direction. The 10 activate function is superior performance in option pricing. This finding underscores the importance of neural network architecture and activate function selection in financial modeling. Looking forward, we envision several key areas for further research. This includes a more detailed analysis of our results to better understand the drivers behind our model's performance, expansion of the dataset, and testing model on the varied market conditions, and further refinement of the model based on the insights we've gained. We also plan to complete and publish our paper contributing our findings to the broader field of financial modeling. In the longer term, we see the potential for continuous exploration and refinement of neural net models in finance. This could include exploring alternative neural network architecture and an ensemble learning method, further pushing the boundary of what's possible in financial analytics. The section 9 is about references. Finally, let's acknowledge the fundamental research and literature that guided our study. Key studies that inform our work include all these listed here. Our methodology and analysis were underpinned by the use of Python and various data visualization tools. A detailed description of the software and tools used offers insight into the practical aspects of conducting such research. This is the end of the video. Thank you for watching.